Hi, I am Vishwanath. Welcome to my YouTube channel. I hope you all enjoyed my previous videos. Today I am going to discuss about the working principle of Wheatstone bridge, working principle of meter bridge and working principle of potentiometer. Let's watch the video and please subscribe my channel. Of X is unknown, that is resistance of DC arm or resistance of X is unknown. The main circuit current I is passing through these four arms I1 and I2 because AB and AB are connected in parallel combination. IG is the galvanometer current. BC carries the current I1 minus IG and DC carries the current I2 plus IG. Okay. At the balanced condition, when potential at the point B is equal to potential at the point D, that is VB is equal to VD, then the galvanometer current IG is equal to 0. Okay. In this case, P by Q is equal to R by X. Since P and Q are known resistance and also R is a known resistance, that's why we can easily find out the value of X. That is, at the balanced condition, P by Q is equal to R by X. Here P, Q and R are known. That's why we can easily find out the value of X. Now I am going to prove this relation. In the balanced condition, current I1 is passing through the resistance P and resistance Q, and current I2 is passing through resistance R and resistance X. That is, P and Q are connected in series and R and X are connected in series, and AC is connected in parallel combination with ADC. ABC is connected parallel combination with ABC. Here we can neglect the resistance of BD in the balanced condition. But in the balanced condition, P and Q carry the current I1. R and X carry the current I2. Okay. Now we can apply Kirchhoff's law in the two closed loop. Therefore, in the closed loop, ABDA, we have Pi1 minus Ri2 is equal to 0. This gives Pi1 is equal to Ri2. Therefore, P by R is equal to I2 by I1. Equation number 1. P by R is equal to I2 by I1. Similarly, in the closed loop BDC, BDCB, we have QI1 minus XI2 is equal to 0. This gives QI1 is equal to XI2. Therefore, Q by X is equal to I2 by I1. Equation number 2. Now, from equation 1 and 2, we have from equation 1 and 2, we have Q by X is equal to P by R is equal to I2 by I1. Therefore, P by Q is equal to R by X. This is our required condition. Good. In the imbalance condition, we can write the I is equal to I1 plus I2. Equation number 1 at the point A. At the point A, I is equal to I1 plus I2. And galvanometer current is Ig. Therefore, P carries current I1, Q carries current I1 minus Ig, R carries current I2, and X carries current I2 plus Ig. Okay. Therefore, for the closed loop, ABDA, we have P into I1 positive plus G into Ig positive minus I2 into R is equal to 0. Okay. That's why I1 and I2 flows in same direction, but I1 and Ig flows in same sense, that is clockwise direction, and I2 flows in anti-clockwise direction in the circuit A, B, D. That's why we consider I1 and Ig is positive and I2 is negative. Where capital G is the resistance of the galvanometer. Where capital G is the resistance of the galvanometer. Where capital G is the resistance of galvanometer. Okay. This is equation number 2. And for the closed loop, BCDB, we have Q into I1 minus Ig is positive, but here Ig and I2 plus Ig flows in anti-clockwise direction, that means they are negative. that is G into Ig minus I2 plus Ig whole into X is equal to 0, because these two loops there is no EMF. That's why we can write Q into I1 minus Q plus G plus X whole into Ig minus X into I2. This is equal to 0. Equation number 2. Okay. In this circuit, there are three unknowns I1, I2 and Ig. If we have the known resistance PQRX. Okay. Now we can consider the circuit A, E, F, C, A, E, F, C, A. And for the closed loop A, E, F, G, okay, A, E, F, C, D, A. We have here I2, and they all are all moving in same direction. Therefore, they are all positive. Okay. If the external resistance is capital R and it is known, then I into R and I into RL, that is external resistance RL. Okay. I into RL plus R into I2 plus X into I2 plus Ig is equal to V. The V is the EMF of the cell. Okay. And we know I is equal to I1 plus I2. Therefore, I1 RL plus R into R plus RL plus X whole into I2 plus X into Ig is equal to V. This is equation number 4. Since I is equal to I1 plus I2. Okay. Solving equation number 2, 3 and 4, we can easily get the values of I1, I2 and Ig if we know the all resistances. Now we can form the matrix of the following equations. That is P, G minus R Pg minus R, Q minus Q plus G plus X. Okay, and this is minus X. In this circuit, this is in this equation RL, this is R plus RL plus X, and this is X. Oh no. I think this is X, and this is R plus RL plus X. The coefficient of I2 who you have to put in this point. And first is coefficient of I1, second is coefficient for Ig, and third is coefficient for I2. Okay, this is equal to 0, 0, V. Now solving this matrix, we can easily find out the values of I1, I2 and Ig. Now I shall discuss about the limitation of Wheatstone bridge. Since at the balanced condition P by Q is equal to R by X, therefore the values of P, Q, R, X should be in same dimension. For accurate measurement, of X, the values of P, Q, R and X should be in same dimension. Okay, therefore if the values of P and Q is very high and the values of R is very low, therefore we cannot get the accurate result of X. Or on the other hand, if the values of Q and R, P or X is very small, then either P or Q or X is very small, then we cannot get the accurate value of X. That's why by Wheatstone bridge we cannot measure very high resistance or we cannot measure. Now I am going to discuss about the working principle of a meter bridge. This is the construction of a meter bridge where AC is a uniform conducting wire. Its area of cross section is same everywhere, and the length of AC is 1 meter. Length of AC is 1 meter or 100 centimeter. Length of AC is equal to 100 centimeter. A scale is placed parallel to this wire, that is AC. That's why we can easily measure the length by this scale. These are the good conductor made of very good conductor, that is copper, and the width of this rod are very large with compared to the wire AC. That's why we can neglect the resistance of this conductor. Now our resistance box capital R is placed between these 2 points, and we can denote this point E and F. Therefore capital R, our resistance box, is placed between E and F, and the resistance of capital R is fixed, and an unknown resistance X is placed between the 2 points M and N. D is the midpoint of F and M, and D is connected with a galvanometer, and another wire is connected with a jockey J and to the galvanometer G. A commutator is connected with the point A and C. Okay. In a commutator, the opposite 2 points are connected with A and C, and the next 2 opposite points are connected with a battery or electric cell having EMF E. At the imbalance condition, current flows through galvanometer. That's why galvanometer shows some reading of current. Now we can displace the jockey touching the wire AC. At the certain point, say this point is B, we can get the null point or balanced condition of this meter bridge. Say length of AB is L1 and length of BC is L2. This is similar to the Wheatstone bridge. At the null point, we can easily find out the resistance of the resistor X. We know that AC is a uniform wire, that's why its resistance is directly proportional to its length. Okay. Therefore, we can write that at the null point, or balanced condition of the Wheatstone bridge or meter bridge, resistance of AB by resistance of BC is equal to R by X, and you know that the resistance of AB is directly proportional to L1 and resistance of BC is directly proportional to L2. Since AC is a uniform wire, therefore RAB by RBC is equal to L1 by L2. Therefore, we can write L1, and you know that L2 is equal to 100 minus L1, where L1 is expressed in centimeter unit is equal to R by X. From this equation we can easily find out the value of X. This is the working principle of Wheatstone bridge. Now I am going to discuss about some drawbacks of Wheatstone bridge or some error about Wheatstone bridge. You know that the Wheatstone bridge or the meter bridge is connected with wire and the rod. At the junction point there should be some resistance at the point A or at the point C, but in the balanced condition we neglected the resistance at the junction point at A and C. That's why there will be some errors in measuring the unknown resistance X. So we have to nullify the errors. This process is known as end correction. Let at the point A the length of wire is joined with the wire is lambda 1. Okay, let at the point A the length of wire is joined with the wire is lambda 1. Similarly, let at the point B the length of wire is joined with the wire is lambda 2. Therefore, the exact result should be R by X is equal to L1 plus lambda 1 by 100 minus L1 plus lambda 2. This gives the accurate result of the value of the unknown resistance X. You know that when the dimensions of P, Q, R, X are same, then the galvanometer or the Wheatstone bridge is most sensitive. Okay, when the dimension of P, Q, R, X are same, then the Wheatstone bridge is most sensitive. If the dimensions of P, Q, R, X were not same, that is P and Q are large resistance and R and X are small resistance. When P and Q are large resistance and R and X are small resistance, then the galvanometer should be sensitive or the Wheatstone bridge should be sensitive when the galvanometer is connected at the junction of PR and at the junction of RX. In this case, the Wheatstone bridge will be most sensitive when they are not in same dimension. Now we are going to discuss about the working principle of a potentiometer. This is a figure of potentiometer where AB is a uniform wire having length L1. In general, its length is equal to 10 meter. AB is a uniform wire or conducting wire having length L1. AB is connected with a electric cell having standard EMF E0, known EMF of an electric cell is E0, and positive pole of the cell is connected with the point A and negative pole of the cell is connected with the point B. This is a rheostat, and E is another EMF in another cell having EMF E. Capital E is the EMF of another cell, and value of E should be determined. The value of E are to be determined. Okay. In this case, the unknown cell is also, or the second cell is also connected parallel with the E0, that is positive pole of the cell is connected with A and negative cell is connected with a galvanometer G, and the galvanometer is connected with a jockey J. You know that by potentiometer we can find out the EMF of a cell. When current, the key is on, the current passing through the circuit and galvanometer shows some current. At the null point, the two currents produced by E0 and E are same and opposite. That's why E1 and I1 and I2 nullifies each other, and the galvanometer current will be 0. Therefore, at the null point or balanced condition, I1 is equal to I2. You know that I1 is equal to EMF by resistance of AB, that is RAB, resistance of AB. I2 is equal to EMF of second cell by resistance of AJ, where J is the null point of this circuit. Now let AJ is equal to L2, the wire of the length AJ, the length of the wire, the portion of the length of the wire AJ is equal to L2, AJ is equal to L2, and the length AB is L1. Since the wire is uniform, that's why we can write that E by E0 is equal to RAJ by RAB. Therefore, E by E0 is equal to RAJ, means L2 by L1. We can easily find out the value L1 and L2 by a meter scale. And if we know the EMF of the first rail or standard cell, that is E0, value of E0, then we can easily determine the value of E, that is EMF of the unknown cell. This is the end of our discussion. I think you all watch my video carefully and understand the discussion. If you like this video, then please click the like button and please subscribe my channel. It's my request, please subscribe my channel. Thank you for watching my video. Okay, goodbye.